Here for this presentation. My name is Andrew Boutros, and I'm going to talk to you today about some of the work that we have been recently doing at the University of Toronto on the exploration of 3D FPGAs. As you have noticed, like all the application designs that we want to implement on FPGAs now are growing in size and complexity, and this really means that there is always an ever-increasing demand for bigger and faster FPGAs. So the graph I'm showing here shows the logic capacity of the largest FPGAs from Xilinx across multiple generations. And if you look at the graph, you notice that as process technology shrinks, it becomes harder and harder to implement larger monolithic FPGAs, which is like a single die FPGA. And mainly that's because of lower yield when you fabricate larger chips. So if you look at the past decade or so, you find that all the largest FPGAs from Xilinx are actually multi-die FPGAs. So they fabricate smaller FPGAs and they integrate them together in the same package using passive interposers, or what they call 2.5D integration technology. And the way this is done is that you fabricate independent FPGA chips and you flip them on top of a passive interposer. And this passive interposer is a silicon die that doesn't have any transistors that do something useful. It just provides high density interconnect between the multiple dies flipped on top of it. So this works, but it suffers from multiple limitations. So the first limitation is that the wires on the interposer are typically longer and slower than the typical wires on the FPGA, so they can degrade performance significantly if the designer doesn't pay enough attention to that. And also the crossings between one die and the other is always concentrated towards the edge of the chip, of every one of the two dies. So this creates placement and routing hotspots because the circuit network primitives are kind of like competing on those precious locations in close proximity to the die crossings. So we believe this can continue to scale, but actually with newer chip integration technologies, now we can integrate or stack multiple dice on top of each other in the third dimension, right? There's the obvious gain from that you get maybe 2 or more than 2 times the logic capacity within the same form factor of the FPGA. But you also, the inter-die crossings or the 3D connections are shorter, faster, denser, and evenly distributed across the 2D area of the FPGA chip. And our focus in this work is to build architecture exploration and CAD tools that can get us to this point. So first, before jumping into the depth of like what we are doing in our work, let me give you a quick overview on how this 3D integration is typically done. So you start by fabricating a normal chip, and the terminology used in 3D integration is typically the side of the chip that has the active transistors is called the back of the chip, and then the side that has the metal stack is called the face. So instead of doing a flip chip where you connect the top metal layer of the chip to the C4 bumps that go to the package for power and IOs, you actually thin down the bulk silicon of this chip and then connect the lowest metal layer of the chip to the C4 bumps using through silicon vias, which are the black columns I'm showing in the figure. So if you take a top view of this die at the bottom, you find that there are a lot of holes in this silicon, and those are the holes that the through silicon vias go through. So you end up with having this checkerboard pattern of holes in the silicon that are typically called the Swiss cheese holes. And then after that, you fabricate some inter-die connections on the top metal layer of that chip and flip another chip on top of it. And now the top metal layers, or the faces of the two chips, are connected to each other, and thus they call this a face-to-face 3D integration. And those inter-die connections are typically fabricated either as micro solder bumps, or if you want denser and higher density of connections, you do direct copper-to-copper connections, which is usually called hybrid bonding technology. So if you look at the pitches for those interconnect density, pitch is the separation between 2 adjacent connections. So the micro bump technology pitches go down from 55 micron to about 10 micron. And then if you want denser connectivity, you move to hybrid bonding, which is usually less than 10 micron and down to about 1 micron. So all the micro bump technologies from 55 micron to 10 micron are relatively mature now. The state-of-the-art cutting-edge technology that we have nowadays is at around 5 micron. And then the 1 micron hybrid bonding is kind of like a research effort that is ongoing, but we're getting there very soon. And just to give you a sense of the density of connections you get with those technologies, so going down from 55 micron to 1 micron, you get somewhere between 100,000 connections to 300 million connections in a mid-size chip that you fabricate. Okay, and then there's another variation of that called the face-to-back 3D integration, but I'm not going to talk about this today. And although all the discussion that I'm going to be going through in the presentation focuses on face-to-face, all the tools that we built are flexible enough and can model both variations of this 3D integration. So really, this opens the door for us to explore new 3D reconfigurable acceleration devices, or what we call RADs. And you can think of those RADs as homogeneous devices where you stack an FPGA on top of another FPGA, or you stack an FPGA on top of an ASIC-based die, and this ASIC-based die can have larger on-chip memories, or a network on-chip for system communication, or any sort of hardware application-specific accelerators on this base die. But in order to explore those interesting devices, we need the tools to do it. So we need tools to model the FPGA fabric itself. We also need tools to model the 3D considerations, things like the area overhead and the speed of those 3D connections and the power distribution networks of those devices. And also we need FPGA CAD tools that understand the 3D nature of the device and can optimize and map those designs to those new 3D devices. So really, our contributions in this work is to develop those tools to enable the exploration of 3D RADs, starting from low-level circuit design up to 3D place and route algorithms. So for those two pieces of the puzzle, we developed a new framework called RadGen, which integrates a tool called Coffee for FPGA fabric modeling, as well as new modeling tools for the 3D inter-die connections and the power distribution networks. And for the third piece of the puzzle, we build on top of the open source VPR flow to make it understand 3D FPGAs. So as you imagine, it's pretty challenging to tell you all the details of the work that's going on to get those tools working and integrated together. So I'm just going to do my best to give you a glimpse of the work that is done on each one of those different fronts. And let's start with modeling the FPGA fabric. So for the FPGA fabric modeling, we build on Coffee, and as I told you, Coffee is a tool that takes as input some SPICE models for the transistors of a target process technology that you want to implement your fabric in, as well as some architecture specifications. It does a lot of SPICE simulations, and with the help of an analytical area model, it models this FPGA fabric. All the full custom circuitry that goes into the FPGA fabric is modeled by that. It also has the ability to model hard blocks that are embedded in the FPGA fabric with a standard cell ASIC implementation flow for the core of the hard blocks, and then full custom circuitry to interface with the programmable routing. So that's Coffee, and in order to model those 3D RADs that we want to explore, we want to model them in a newer process technology. So we first upgrade Coffee to use a newer 7 nanometer process technology, and then also upgrade the area model that is used to be more suitable and more accurate for FinFET technologies instead of bulk transistors, and also be aware of all the metal limitations that come at advanced process technology like 7 nanometer. And then we use Coffee, this enhanced Coffee that we do to optimize the FPGA circuitry at 7 nanometer and study the trade-off between different circuit design styles. So like FPGAs traditionally use pass transistor circuits. They use fewer transistors but are trickier to design and less reliable in advanced processes. And this was achieving the better area delay product until the most recent study in 22 nanometer. But then we found that this flips in a newer process technology, and now transmission gates achieve a better area delay product, even though they use more transistors. Okay, so now we modeled the FPGA fabric, but we need to think about how do we implement those 3D connections between the two dies. And there are so many possibilities that we can do, and there's a lot of trade-offs between them. So for example, signals can cross between dies at the input of FPGA blocks, or maybe the outputs of an FPGA block crosses from the upper die to the lower die to connect to the switch box of the programmable routing. Or you can have something like a 3D switch box in the FPGA that gives you the full flexibility to cross from one die to the other at any intersection of routing in your FPGA. So the tools that we build give you the ability to kind of like explore those different options and other ones that you might think of and study the trade-offs between them. So as a start, we start with the output, modeling the output crossing one, because this is the most straightforward to think about and the easiest to model. But we already have results for the other options that will be published soon in an extension to this work. Okay, now that we have the FPGA tile areas that we got from Coffee, and we know how many die crossings do we need to have in the output crossing options, we can start reasoning about what 3D integration technology do we really need to make this homogeneous integration feasible. So if you look at all the microbumps technologies from 55 micron down to 10 micron, this can provide at most 15% connectivity between the two dies, so it's very restrictive and unlikely to work in most cases. If you look at the next generation, the 1 micron hybrid bonding, this can provide full connectivity for the two dies, which means that all the outputs of all the blocks on one die can cross to the other die and connect to the switch boxes on it. But the state-of-the-art cutting-edge technology that we have nowadays is not enough. It provides about 60% connectivity between the dies, so it could work with some restrictions, but it needs some evaluation from the CAD perspective to see if this limitation really affects the quality of results when mapping, placing, and routing designs on those 3D FPGAs. So now moving to the second piece of the puzzle, where we start modeling the 3D considerations. So we need to answer 3 key questions. So how fast or slow are the 3D connections from one die to the next? What is the area overhead of the drivers or the buffers that we have to add for those connections? And also how much of the base die area is taken out because of those Swiss cheese holes that are needed for the through-silicon vias for power delivery and IOs. So we built very complicated circuit models for those 3D connections, and we even add, we pay attention to some practical considerations like circuitry that you need to add to protect against electrostatic discharge while fabricating those devices. And this really helps us answer a couple of questions. So the first question is like, how slow are those connections in the third dimension? And actually they are pretty fast. So it's about 50 peak per second to cross from one die to the other, which is equivalent to a normal FPGA wire of length 4 blocks. And also, it turns out that the driver and the electrostatic discharge circuitry can add around 4% additional area to your FPGA tile if you go with the most aggressive protection circuits against electrostatic discharge. But if you get rid of those electrostatic discharge circuitry, this overhead goes down to less than 1%. So this is something for the manufacturing engineers to think about on how to shrink those electrostatic discharge circuits. There are way more details about this in the paper, so please go check it out if you're interested. We also modeled the 3D power distribution network of those devices, so how do we deliver power to those two dies in order to figure out how much area is taken out by those Swiss cheese holes, and we find that it's somewhere between 3 and 10% of the base die is unused because of those Swiss cheese holes, and it depends on the 3D integration technology you want to use and the IR draw that you're targeting for your power distribution network. Again, more details in the paper. And then the final piece of the puzzle is the FPGA CAD tools, but in 3D. And we built on the top of the open source, widely used VTR flow to make it understand 3D FPGAs. So this involves work in extending the architecture description language of VPR. So now users can specify devices that have multiple layers, and those layers can be conventional FPGAs or other or layers that have other hard blocks or network on chips and so on. And then users can also define flexibly the connectivity between those two dies, what signals cross from one die to the other. And also, the work involves a lot of extensive changes to the placement and routing engines inside VPR to make it understand the 3D nature of the device and how to optimize the mapping of any design that you give to it to those 3D devices. So all those changes that we do to VTR are merged to the VTR master branch, so any future development on VTR will build on top of those changes. So that's why we made sure that those changes have no effect on the quality of results and minimal effect on runtime if you want to do experiments on 2D conventional FPGAs. Okay, so now we have the full stack of tools to model those 3D RADs. So let's go back to what we wanted to model at the first place, those two interesting variations of devices. So for the first case study, we compare a conventional 2D FPGAs to a 3D FPGA that has the same number of logic resources on it. And remember when I told you about this tricky problem with the current technology that we have, that was limited connections, we need to evaluate the feasibility of this from a CAD perspective. So now we have VPR 3D, so we can go back and evaluate that and the effect of it on the quality of results. So I'm showing here the results in terms of normalized critical path delay and normalized routed wire length for a wide variety of applications from the COIUS benchmark suite. And those benchmark circuits are actually, some of them are pretty big, so up to like more than 1 million netlist primitives. So you can see that once we move from 2D to 3D, we actually get gains in terms of the quality of results. So 2% better critical path delay and 6% better routed wire length. So those are already by themselves decent gains in terms of quality of results, but this is really not the reason why you would go and build a 3D FPGA. The key takeaway here is that 3D stacking can help us significantly increase the logic capacity of the device while improving the quality of results, which is not the case of what we have now in 2.5D integration. And then the second case study that we do is comparing a 2D FPGA that has embedded network on chip routers in the fabric compared to a 3D RAD that has the network on chip on the base die along with much larger on chip SRAM memories. And in order to evaluate that, we actually go and build an application to be a benchmark for it. So we build a streaming deep neural network accelerator that has a bunch of processing elements talking over the NOC. So we can take this and use it as a benchmark. And we show actually you get a lot of significant gains in terms of critical path delay, because now this humongous block, the NOC router block that is the yellow box, is now moved to the base die, and the fabric is more regular with less disruptions. And if you look at the area breakdown of this base die, so we actually managed to manually floor plan SRAM macros and NOC routers to kind of like circumvent those holes that are colored in black. And we managed to fit more than 130 megabytes of on-chip SRAM in this device, and this takes about 56% of the base die area. And then there's 3.2% and 3.6% for the NOC and all the Swiss cheese holes on the base die. And this really leaves you with about 37% of empty space on the base die. And those are the white kind of like spaces between the different macros that we floor plan. And here's a suggestion on what you can do with this 37%. We managed to add like 3,000 FP16 dot product units to the device. And this is equivalent to more than 180 tera operations per second of additional compute that you can put on the base side for applications like machine learning and deep learning acceleration. Okay, so what are the key takeaways of this talk? So we now have a full stack of tools that can help us model those 3D reconfigurable architectures. 3D integration is feasible and actually works well on the case where an FPGA is integrated on top of another FPGA, but there's a lot more to explore in terms of the circuit design, the architecture, the CAD, and how to make this work better. 3D integration also opens the door for a completely new class of devices that integrate FPGAs on top of ASICs. And we have tools to model that. So there's actually another tool that I didn't talk about today called RADSIM, an architecture simulator for RADs that can help us along with RadGen to explore this device. So thank you for your attention. All the tools that I have talked about today are actually open source, so you can scan the QR code to use them, but we use Homer Simpson, but he's not open source. And Fox has the copyrights until 2082 at least.